Greetings, welcome to lecture number 23 on basic circuit theory. I am Razavi. Today we will continue to look at one more example of RC circuits before we finish up this topic, and then go on to inductors and RL and RLC circuits. So we'll take a look at inductors today just to familiarize ourselves with their properties, and maybe look at a very simple RL circuit, and then this will open up our discussion for other lectures in the future. But before we go there, let's take a look at what we covered last time. We had two examples of RC circuits. We saw that in the circuit we first apply a step and let this capacitor charge to some voltage. So the voltage on the capacitor charges up to some value. It is headed towards V1, the maximum value, but before it reaches there, at some point T1, this switch begins to conduct and introduces R2 in parallel with the capacitor. As a result, now the circuit changes its properties. The time constant changes from R1C1 to R1 in parallel with R2 times C1, so time constant goes down, and also the final value that V out and VA can reach goes down, because now we have a voltage divider at time infinity. So the output voltage is 0 up to T1, and then it jumps to this value, and now V out and VA have the same value, and they go together towards this final value, whatever that might be. The second example started with some simple capacitor circuits and the response to a step input. And we saw that in these cases, the current has to be an impulse, because we're trying to change the voltage across a capacitor or a series of capacitors in zero time, and that results in an impulse. So we also saw that the voltage in this case also has a step behavior. So V out jumps in zero time, but not as much as the input, because these two capacitors act as a voltage divider. So we see that the output voltage is given by the input step height times this attenuation factor. So today we'll start with this example and add a resistor here and see that things become much more interesting. So let's go ahead and do that. So we have this example where we again have a step. So Vn is equal to V1 U of t, and this step is applied to a capacitor C1, another capacitor C2, and a resistor R1. And we are interested in this voltage here as a function of time. Okay? So with the evolution that we followed last time, we can try to guess what V out should look like, and then of course write the equations and solve it. So we saw that without this resistor, this voltage jumped, not to the full amount of V1, but to a fraction of it. The question is now that we have this resistor, does V out still jump or not? So you have to think about that for a moment and decide. Okay, well, let's assume V out does not jump. Okay, we'll see what happens. The circuit doesn't bite. We can always start with some assumption and see what happens, right? So we say if V out does not jump, it means that C2 at 0 plus still has 0 volts on it, right? Okay, so this has 0 volts on it. How about C1? Well, at 0 plus, this is equal to V1 volts, right? The input has jumped to V1. This is equal to 0. So C1 experiences a voltage change of V1 in 0 time. So we say C1 has a voltage change of V1 in 0 time. Okay, that's the key. Why? Because the input jumped. This hasn't jumped, that's our assumption. So the voltage on this capacitor jumps by an amount of V1. If the voltage on the capacitor jumps, what happens? Well, if the voltage on the capacitor jumps, the current through the capacitor has to have an impulse in it, right? That's what we saw last time. So we say that this current, let's call it I in has to have an impulse, right? Has to be proportional to an impulse. There's no other way. To charge a capacitor in 0 time, we have to have an impulse. All right, so we are drawing an impulsive current from the voltage source through C1. But where does that current go? Can that current go this way? No, because an impulsive current through a resistor gives us infinite voltage. But we don't have an infinite voltage available, right? This is only V1 volts. There's no other source of voltage. So we cannot possibly generate an infinite voltage in the circuit. So we say I in cannot entirely, okay, let me clean this up a little bit. So we say the impulse cannot flow through R1, otherwise it would create an infinite voltage. Okay, so an infinite voltage is not possible in a circuit where all the voltages are finite. The only possibility to create an infinite voltage in a circuit is to have a current source whose terminals are left open, remember? So if you have a current source that goes through a very, very, very large resistor, then it's going to generate a very, very large voltage. But in this circuit, that's not possible, right? So we cannot have an impulsive current through R1 because there is no source of infinite voltage in the circuit. Okay, so then the question is, where does that impulse go? You have an impulsive current coming in. It cannot go this way. It has to go through C2. So this line of thinking tells us that impulsive current must flow through C2. All right, even though the resistor is there. So right between 0 minus and 0 plus, the resistor doesn't really play any role because the impulse of current that's flowing through C1 also flows through C2. So how much is the voltage across C2 at time 0 plus? Well, that should be the same as what we found before, right? Before, without this capacitor, without this resistor, we found that this voltage was a step with a height that is less than this height due to this capacitive divider. This time we should have the same thing. Why exactly? Well, because the charge that is delivered by this voltage source to the circuit between 0 minus and 0 plus entirely goes through this capacitor and this capacitor. It cannot go through this resistor. Why? Well, let's calculate. So we say charge delivered to R1 from 0 minus to 0 plus, right? 0 minus to 0 plus. So it's integral of 0 minus to 0 plus of the current flowing through the resistor, some IR1 times dt. Remember, charge is integral of current with respect to time. Okay, now we decide that the current through R1 is not an impulse. If there's any current, it has to be finite. It cannot be infinite. And because we have a finite amount of current, and we are integrating it across a very, very, very short amount of time, the result will be close to 0. So we say this is 0. So the charge delivered by this voltage source has to go on to only C1 and C2, because during that very short time period, no charge has been delivered to R1. So all of it has to end up on these two. So during that very short time period, R1 plays no role in the circuit whatsoever, as if it were not there, as if it were infinite. So we can say that the voltage on C2 still jumps by the same amount that we calculated last time. So we say VC2 at time 0 plus is equal to V1 times C1 over C1 plus C2. Okay, so you can see that this line of thought is necessary to get to this result, right? Even if you sit down to write equations, equations won't tell us everything that we have here, right? Some of this just has to come from thinking. There's no other way. So it all goes back to C dV over dt, right? And all the conditions that we found last time in this example. All right, so then we can try to sketch VC2. Of course, VC2 is the same as V out, right? So we say V out. And what we observe looks like this. So we had 0 before time 0, not a problem there. And at time 0, we decided that this voltage has to jump. Just like before, without R1, right? It jumps to this value here. And now the question is, what happens after this point? Okay. All right, so we're going to look at the circuit a little while and understand exactly what will happen. This voltage is now V1. It's a step, right? It's like a battery, V1. This capacitor has some finite voltage on it, this much. And now we have this resistor. So our expectation is that this resistor will discharge these capacitors over time. It wants to draw some current, right? Any finite voltage here results in a finite current, so R1 begins to discharge these two. But we have to be careful here. So let's think about it as follows. What we know is that at time infinity, probably all the voltages have stabilized. They are constant. And we know that if the voltage on a capacitor is constant, the capacitor acts as an open circuit. So if that is the case, this capacitor is an open circuit, and so is this capacitor. So what can I say about V out at time infinity? At time infinity, this is not here. There's no conduction here. This is not here. There's no conduction here. You have this resistor sitting dangling by itself. It has no current. It has no voltage. So our prediction is if all voltages become constant at t equals infinity, then C1 and C2 are open, right? They're open circuits. And that means that all we have is a resistor like this, R1. There's nothing connected to it, so V out has to be 0. So in the extreme case, this voltage has to approach 0 here. So that is our prediction. And we might say, okay, it probably goes like this, right? We just have to see if that's true. Okay? So what the circuit does is it takes part of the step and brings it over here, right? This much of the step. And then it exponentially decays, right? As the capacitor charge and discharge, eventually everything goes to, the output goes to 0. Okay, can I express the output as a function of time? Yes, this is a first order system. And because the first order system still satisfies the equation I showed you last time and times before that, right? So y is equal to y infinity plus y0 minus y infinity times the exponential. So it's the same thing here. But you may ask, why is this system of first order, even though it has two capacitors in it? All right, so let's investigate that. Okay, so why is this system of first order? Okay, well, we talked about this a long time ago. We said that when we have a linear system and we write the differential equation for it of order n, to solve this differential equation completely, we need n initial conditions. And those initial conditions have to be independent, meaning that you cannot get one initial condition from the other ones, right? All of them have to be independent. We should be able to enforce all of these n independent initial conditions without any conflict. So here in this circuit, what we can see is that if I have an initial condition on C1, the initial condition on C2 is known. It cannot be independently set. Why? Okay, well, that's easy. Let's change the color of our pen. Okay, to this color here, maybe. Okay, now maybe do this color. Okay. So suppose before I apply this step, right, when this is 0, I come along and say I would like to have an initial condition of 2 volts across C1. Okay? So I say this is 2 volts. So remember, I'm trying to solve a differential equation. That differential equation requires n initial conditions. So if I'm thinking that this is a second order system because it has 2 capacitors, then I should be able to enforce 2 independent initial conditions. So I enforced 2 volts across C1. Can I impose a new independent initial condition across C2? Let's go ahead and do that. So let's say this is 5 volts. Okay, so I decided that I would like to have 2 volts on this, 5 volts on this. And if they agree, if there's nothing wrong with the circuit, no problem, we have a second order system. But is that true? So before time 0, this is 0, right? The step is 0. So I should be able to write the KVL here. 0 is equal to this voltage plus this voltage, right? So KVL, maybe I write here. So KVL. So here's the situation. I have C1, 2 volts on it. I have C2, 5 volts on it, right? And I have 0 because we are talking about time 0 minus before the step comes in. So a KVL here says 0. This is equal to this plus this. 2 volts plus 5 volts. So you see that we have a problem. So we cannot set the initial conditions of these two separately. In other words, as soon as I call this 2 volts, this has to be minus 2 volts. There's no other way because this plus this has to be 0, right? Okay, so we see that only one initial condition can be applied independently. So only one initial condition can be applied independently. And that's why the system is of first order. Okay, that's great. All right, so now I can use my standard equation to solve the circuit, right? So we need the following. We need y infinity. How much is y infinity? Y infinity is the amount of this quantity of interest at time infinity. We decided that it has to be 0 from this little analysis here. So it's 0. Y0, or 0 plus. How much is y0 plus? How much is this voltage at time 0 plus? We found that. We found that here is this value here. So V1 C1 over C1 plus C2. How much is the time constant? Well, that's a little trickier, right? Because we have two capacitors. Previously, our computation was to take the capacitor out and find the resistance, but now what do? Well, not a big deal. Let's take our time. We follow the same procedure. First, we set the independent sources to 0. So, tau. Set independent sources to 0. Okay, so you set this to 0. What do we get? We have C1, C2, R1, right? Can I find the time constant of the circuit? Sure. What happens is that when I go to this computation topology, C1 and C2 actually appear in parallel. So I can just say the time constant is given by the sum of these two capacitors times this resistor. So we say tau is equal to R1 C1 plus C2. Sounds like magic, right? It's interesting that it happened that way. So does it mean that in all first order systems, when we set the independent source to 0, we end up with something like this, where all the capacitors merge into one, and we have a single capacitor, single resistor? Not really. That's not true all the time. So in general, if we want to find tau, we have to write the differential equation. Differential equation will be of first order, and I showed you a long time ago how to compute tau from the differential equation itself. But in cases like this, we just go with our method of finding time constant by inspection. Okay? But if you have determined from this type of analysis that the system has an order of 1, but finding time constant seems tricky, you just have to write the differential equation for the system, and then from there calculate time constant. Okay, so we have found the time constant. Now we can write V out, right? So V out as a function of time is given by infinity value, which is 0. So it would be just really this one, which is V1 C1 C1 plus C2 x power minus t over tau and u of t. Right? It's just a simple exponential decay. All right. I encourage you to compare this circuit with another circuit that we had before, where we did not have this capacitor. Do you remember? We had a single capacitor, a single resistor. Go back and compare the results of this circuit with the results of that circuit. That's also very interesting. Okay. This concludes our study of RC circuits. There are many more interesting examples, but in the interest of time, we'll have to move on to inductors and explore those devices as well. All right, so let's talk about inductors. Of course, you've seen inductors in physics. You have some idea as to how they operate, etc. So we'll just review some of those concepts first and try to frame their operation in our own language, in the language of circuits, and then try to build circuits out of inductors and resistors and eventually capacitors as well. But I wanted to show you something that is very interesting. So here's a piece of wire, right? As you can see, that's a piece of wire. It has these two ends. So this looks like a pretty good short circuit, right? You can try to connect 2 points of a circuit together, right? It's a short circuit. If you want to be more precise, you can say that this wire has some resistance associated with it, so it satisfies Ohm's law, right? So if you apply some voltage between these two ends, we're going to get a current, and that current is given by the voltage divided by the resistance. All right, so that's nothing surprising. But let's take this wire and do something like this. I'm going to take this wire and I'm going to wind it around this pen. All right, I hope you can see what happens here. So we wind it around this pen, and this is what we get. What is this? This is an inductor. So what happened? We had a piece of wire. It satisfied Ohm's law. But by just reshaping this wire, we created a device that doesn't satisfy Ohm's law. And that's the fascinating thing about this and about magnetism, because this all relates to magnetism. Okay, so what really happened was up to the end of the 19th century and the beginning, to the end of 18th century and beginning of 19th century, people knew about electricity, knew about batteries and so on. They also knew about magnetism. You had magnets and they repelled or attracted each other and so on. But no one had connected electricity and magnetism together. They seemed two completely separate and independent phenomena. But then around 1820, a Danish scientist named Ørsted accidentally found out something interesting. He saw that, 1820, he saw that if we have a piece of wire and we pass a current through it, he saw that there was a compass here, and the compass was pointing, for example, to north and south like this, right? And he saw that when there's a current through this wire, the compass deflects. It changes its direction. Now, they knew that the compass was made of a magnet. So his conclusion was that if there's a magnet and we pass a current through a wire, this magnet is affected by this wire. And what that means is that this current through this wire generates a magnetic field around itself. And that magnetic field, like the Earth's magnetic field, interacts with this compass and deflects the needle on the compass. All right, so Ørsted said that if you have a piece of wire and you pass a current through it, we generate a magnetic field, and that's how our right-hand rule comes into picture. So we generate a magnetic field like this in the form of a circle around this piece of wire if the current is passing through the wire. So any object that has any magnetic properties and is placed inside this magnetic field will be affected by it. So that was the first connection between electricity and magnetism. That was very interesting. All right, but that still doesn't come into picture as far as inductors are concerned, right? At least not as far as circuits are concerned. So something else was needed to be discovered, and that was discovered by Faraday. So sometime later, I don't remember when, Faraday discovered something interesting. So Faraday said, sure, Ørsted is right. When we have a current passing through a wire, it does generate a magnetic field around the wire. But if the current is changing with time, which means the magnetic field is changing with time, then something even more interesting happens. So here's our good old wire with a current, I, but now I is a function of time. And we have a magnetic field around it that's also a function of time. So if what happens now with this magnetic field that's changing with time is that if I place another wire in the circuit, so let's bring another wire. Okay, just a wire by itself. It's not connected to anything else, right? I bring another wire, and what I see is that this wire begins to develop a voltage across it. That's fascinating. There's a piece of wire. It doesn't have any current through it, but it has a voltage on it. Certainly not Ohm's law, right? So, in summary, this is what happens. You have a first wire. Through the first wire, we pass a current, and we let the current change with time. So the magnetic field around this wire begins to change with time. Now we bring a second wire, the red wire. Bring a second wire, just place it in that field. That second wire begins to generate a voltage across itself, right? And that's what we call induction. We have induced the changes in this current through this magnetic field onto this wire, to the red wire. So we have induced a current, we have induced a voltage from this to this, from the first wire, the green wire, to the red wire. So that eventually becomes a very interesting concept. It relates to transformers. So you can build a transformer like this. I don't know if you've seen that in the past or not, but transformers are used in many different systems today, including power systems, etc. So you see that there's an inductor on this side, there's an inductor on this side. They're not connected. And if I pass a current through this, and that current is changing with time, I get a voltage here, even though there's no current through this part, right? So that's the interesting and beautiful result of this relationship between electricity and magnetism. We can create magnetism from electricity, right? Passing a current gives us a magnetic field. But we can also generate electricity from magnetism. If I have a magnetic field that's changing with time, I can generate a voltage, I can generate electricity. So this relationship between the two became an important and solid foundation for everything that we do today. All right, so, but how does this help us with circuits? Well, one thing that becomes interesting is that if I have a piece of wire, so let's go back to the green wire. If I have a piece of wire and I'm passing a current through it as a function of time, so this piece of wire is generating a magnetic field. So there's a magnetic field like this, and that magnetic field is also changing with time. All right? So if I have a piece of wire that is immersed in a magnetic field that is changing with time, that piece of wire should generate a voltage, right? So in other words, we don't have to have a second wire to generate a voltage. Even if you have a first wire, and even though that wire is creating its own magnetic field, that magnetic field can induce a voltage on the same wire. Okay, so here we have two wires. We induce the voltage from the first wire to the second. Here we have a single wire, and this single wire generates a voltage across itself, provided that the magnetic field is changing with time. And that happens when this current is changing with time. All right, so let's make sure we understand this. If the current doesn't change with time, the magnetic field doesn't change with time. And there's no voltage here. It's just a simple piece of wire, ideal piece of wire. We have a magnetic field, everyone's happy, nothing is changing. But if the current is changing with time, and as a result, the magnetic field is changing with time, then this wire develops its own voltage here, some voltage V. Okay, even though it seems like an ideal wire. So it definitely does not satisfy Ohm's law. So from another perspective, if we have a piece of wire that carries a current, if you have a piece of wire that carries a current, and the current is not changing with time, then that piece of wire is just an ideal piece of wire. It's like this, right? Just a simple short circuit, doesn't do anything. But if the current through a wire is changing with time, then that wire begins to have inductance associated with it. So even though this piece of wire doesn't look like an inductor, it is actually an inductor as far as the time varying current is concerned. And that's what we want to study now. Okay, so let's go ahead and go to the next page here. All right. So, inductor basics. All right, so the symbol that we have for inductor looks like this. And we have some sort of voltage here, V1, some sort of current here, and this inductor has a certain inductance value L1. And these three are related by a very simple equation that comes from physics. We won't bother explaining it. We won't bother trying to make it as intuitive as was the case for capacitors, right? It's a little less intuitive. It has to do with the magnetic flux. But we don't repeat all of that. We just accept the final result. The final result is that these three are related as follows. The voltage across the inductor, so V1 is equal to L1 dI1 over dt. Okay, so this partially agrees with our basic understanding that I just mentioned a minute ago, right? It says that if the current through this structure doesn't change with time, right, the current doesn't change with time, there's no voltage. The voltage is zero. So if there's no current through the structure just looks like a piece of wire, right? Because only a piece of wire can guarantee a 0 volt difference between these two. All right? Okay. On the other hand, if the current through the structure, through the inductor, is changing with time, and it has some finite derivative, then we also have some finite voltage across this device, as if it were a resistor, even though it doesn't satisfy Ohm's law. So this will be the important equation related to inductors, just the way I equals C dV over dt was the important equation for capacitors. So pretty much everything we said there applies here, except that things are turned around, right? Here, voltage is proportional to the derivative of the current. For capacitor, it was the current that was proportional to the derivative of the voltage. But so long as we keep these in mind, we understand how inductors operate. All right, so two important results. So we say if V1 less than infinity, right? So if the circuit containing this inductor cannot give it an infinite voltage, then this derivative cannot be infinite. This means that I1 cannot jump. So I1 cannot jump in 0 time, meaning it cannot jump instantaneously. All right? So that is in contrast to behavior of the capacitors. For capacitors, the voltage could not jump if the available current was less than infinity. Here's the other way around, right? The current cannot jump if the voltage available for that inductor is less than infinity. Okay, the other extreme is if the current is constant. So if I1 is constant, then V1 is 0. So this inductor guarantees a 0 volt difference between here and here. And what is that type of device? That type of device is a short circuit, right? Just like this. So we say that L1 is equivalent to a short circuit. So those are the two extremes. For capacitors, we also saw something similar, except that, of course, the situation is different. So in all of the RL circuits and RLC circuits that we'll study in the next few lectures, we have to keep both of these in mind. This typically happens when there's a switching event, something is switching in, something switching out, or when there's a step somewhere. And this typically happens near the end when things have settled, no current is changing with time, so the voltage across the inductor is 0. So, but we always have to remember these. Again, if you don't remember them, you go back to the original equation for the inductor. All right, so just the way there was room for confusion for the polarity of currents and voltages of capacitors, there's confusion here as well. So we have to make sure that is clear. So again, we are assuming that the current goes from high potential to low potential. All right? So that's how this equation comes about. If we have, for example, something like this, and the current is like this, and the voltage we have assumed like that, right? If I choose these arrows and directions as shown on this diagram, then I should say that I1 is going from low potential to high potential. And that means that V1 is equal to minus L1 dI1 over dt. So again, you have to go through all the exercises that I mentioned before for capacitors to make sure that you master this polarity and you don't get confused. All right. And one last point is that if we have the voltage of an inductor, we can find its current, right? So we say to find the current of an inductor, we just say we need this current, so we say I1 is equal to 1 over L1 integral of V1 dt. So the current through an inductor is given by the time integral of the voltage or the area under that curve divided by the inductance value. Okay, so that's how we can find that. So we can always go back and forth between the current and the voltage according to this equation or that equation. All right, so let's see what else we have here. Okay, let's look at some examples. Actually, one more point. So one more point. So we saw that an initial condition on a capacitor was clear, right? We have a capacitor, there's some voltage difference or some charge here, positive charge here, negative charge here. That was the initial condition. For an inductor, it's a little different. For an inductor, initial condition means the current through the capacitor, through the inductor, is not zero. So the initial condition is like this. We have an inductor, L1, and it just happens that at the moment we look at it, there's a current I0 here. And that would be the initial condition of the inductor. So in any circuit that we are solving, for example, you have a differential equation and you're trying to find initial conditions. The initial conditions to look for are the voltage on capacitors and the current through inductors, right? Not the other way around. That doesn't work. Okay, so with that, we can just look at some simple examples to warm up as far as inductors are concerned. So here's an example that I have here. Suppose I have a current flowing through an inductor that looks like this. Call it alpha T. It's a ramp that is applied to an inductor. Okay, I1. And I am interested in the voltage across the inductor. Because the current is changing with time, there must be a voltage, right? So let's try to find the voltage. Okay, so we say the voltage is equal to L1 dI1 over dt, and that's equal to L1 times alpha. So I can plot the voltage. The voltage as a function of time. Before time 0, the current was constant. It wasn't changing. It was 0 anyway. So the voltage is 0. And now we have a constant derivative. The derivative is alpha and then multiplied by L1. So V1 is constant. So we generate a constant voltage across the inductors. All right, so in response to a ramp, a ramp current, an inductor generates a voltage that's constant. Strange but true. So that's what it does. So we see that the voltage across an inductor can jump. Nothing wrong with that. But the current through an inductor cannot jump, provided that the voltage available for the inductor is not infinity. Okay, let's see. All right, one more point. What happens if I make this current slope higher and higher? If this becomes sharper and sharper? we can see that this voltage goes up, right? Because this is given by alpha 1 times alpha. So the sharper this current changes, the more sharply this current changes, the higher this voltage will be. We generate a larger voltage across the inductor. And that again makes sense. So the faster we change the current, the larger the voltage drop across the inductor. And that sometimes is useful, sometimes is harmful. And we'll see examples of that in the future. I will see you next time.